All right, thank you. You should see the little dot up there that says we're recording now. Perfect. So we'll go ahead and get started. I think these were the molecules we had looked at. And I think we had actually already looked at what the intermolecular forces were on these. Is that correct? Feel free to just yell things out, right? We don't have to be polite. It's just us here. We're a small enough group.
I think we did towards the end of class.
Okay, I thought that's what we had ended with. Perfect. All right, so let's go ahead and put those in there. Just kind of remind us with these four molecules, the one with the strongest intermolecular forces was ethylene glycol. It had lots of hydrogen bonding and a big molar mass. Water also had lots of hydrogen bonding, but it was tinier. So it had a smaller London dispersion force. So we put him in second place. And then ethanol, which only can form one hydrogen bond. And then lastly, diethyl ether, which only has polar qualities there. So when you finish drawing that Lewis structure, you can see that it's bent around that oxygen. So our polar bonds do not cancel. And we end up with an overall polar molecule. So it will show dipole kind of interactions for its strongest intermolecular force. Okay. So I don't think that we had a chance to look at this graph. Is that correct? All right. You're going to be a quiet group tonight. All righty. Yeah, you can use the chat box. I do have it open, so I can see any messages in there. So when we do the class participation questions, you can just type your answer into the chat box, so I can get a sense of, if things are going well or if we need to backtrack and review some concepts. All right. So this graph is for those four molecules that we just looked at. So I want to kind of point out some features with vapor pressure and boiling point on here. So we kind of see again how vapor pressure, that property, is inversely related to intermolecular forces, right? So we've got those 4 points on the side there. So the first thing to notice is that for any of the compounds, right, so any of those lines on our graph, as the temperature is getting larger, the vapor pressure is increasing, right? So what does that make sense? Let's think about it. So when the temperature goes up, what's happening there is the molecules are getting more kinetic energy on average, so they can overcome those intermolecular forces, and more of them end up in the gas phase. So that means more vapor pressure. So for all of these materials, as the temperature goes up, the vapor pressure goes up. Note that it's not a linear function. It's not a straight line function. So in just a little bit, we'll come back to that and look at the math for that. And it's a different kind of math than we've done before. So we'll look at that functional group right now. So let's just focus on the qualitative aspects of it right now. All right. At any temperature, though, if we just pick a temperature like 40 degrees and look at the vapor pressures of all the different materials for a given temperature. So for example, at 40 degrees, our ethylene glycol doesn't really have a vapor pressure. It doesn't really register. So most everything stays in the liquid phase, right? Water has a little more vapor pressure, and then ethyl alcohol, ethanol, and then diethyl ether. So again, we're seeing that for a particular temperature, the things with larger intermolecular forces, like ethylene glycol and water, have smaller vapor pressures. Right? So we can just kind of see that acted out on our graph here. The new thing here that we haven't really mentioned too much before is that when do things boil, right? So boiling is converting your material from a liquid to a gas. So that happens when the vapor pressure, right? So remember, that's the pressure of our gas that's just naturally on top of our liquid. when that vapor pressure is large enough to equal whatever's going on in the atmosphere, right? So whatever atmospheric pressure is. Right? So we have on that graph, kind of near the top, something called the normal boiling point. And that happens when the vapor pressure gets to be 1 atm. That's kind of normal, typical conditions here. So normal boiling point is what's the temperature when the vapor pressure gets to 760 torr. And that's different for these different materials, right? So the ones that have very low intermolecular forces, they're going to boil at lower temperatures. Their vapor pressure is going to be high enough at a lower average kinetic energy. So diethyl ether has the lowest normal boiling point, right? And it just increases as those intermolecular forces carry on. All right, so I think that kind of covers all the points on this graph. Is there anything else you're seeing that you want to ask about? We'll just kind of beat we'll beat vapor pressure to death here because it is, like I said, it's the one that's kind of backwards there. So we'll practice. All right, so if you are close to your chat box, you can just type in the letter of the answer that you think this is. So which of these compounds has the highest surface tension? We'll wait for everyone to get their votes in. Oh my goodness, we have a bunch of people who will not be voting today. I can tell it's going to be a tough crowd. So if we're looking for something, thank you. I knew somebody would vote. Right, the highest surface tension, right? So that's the strongest surface tension. All right, so a big surface tension, right? That's going to be something that has a very large intermolecular force. Right? So the idea then is we're going to look at our, yes, there you go. Yeah, we are going to see a hydrogen bond with our ammonia. We're going to look for things that have a large intermolecular force. So for us, ammonia, right? Let's look at that one. Think about the kinds of intermolecular forces it has in it. Think about the strongest one it has. That's really what we're going to focus on. Okay. NH3 can form hydrogen bonds. Can PH3 form hydrogen bonds? Not at all, right? Can PCl3 form hydrogen bonds? No, right? Only ammonia can form hydrogen bonds. Remember, that's a very strong intermolecular force. So if we have ammonia there, it's going to have the strongest intermolecular forces. Right? Can you think about the intermolecular forces that the other two compounds would have? Right? What does PH3 have? What kind of intermolecular forces does PH3 contain? Okay. Okay. All right. PH3, you want to think that it has a dipole force, but it doesn't. So PH3 is that weird one that we talked about a while ago. We forgot about it. PH3 contains bonds between hydrogen and phosphorus. And remember what we said about hydrogen and phosphorus. They have exactly the same electronegativity. So their bonds are not unfairly shared at all. Those electrons are shared perfectly fairly. It doesn't have any polar bonds, so it can't be polar. Like that's not an option for it. PH3 has only London dispersion forces. PCl3, which has a very similar shape, is a polar molecule though. Phosphorus and chlorine bonds are polar, so, and they're arranged not symmetrically in that compound. All right. So for us, the ones with the strongest intermolecular force, right, that's the one with hydrogen bonding. That's much stronger than all the other choices. Excuse me. So if we ranked these, we put them in order, right? We weren't asked to do that, but we could. Right? We could put them in order from the strongest kind of intermolecular forces, which would be NH3 with hydrogen bonding. And then PCl3 has the next strongest kind of force with dipole forces. And then lastly is poor PH3, who only has London dispersion forces. All right, you have questions on that one? So that's our goal here with these. We're starting to put it all together. Okay? So we want to look at our compound, decide what kind of forces it has in it. And in order to do that, you need to know something about its structure. What elements are bonded to what other elements? What's the overall geometry? How are the bonds distributed? Is it polar? Is it not polar? We have to think about all those things to determine what kind of intermolecular forces are in that compound. And then we have to apply that knowledge about the forces to the properties. So we have to know how the properties are related to the intermolecular forces. All right, so let's try another one. Oh, it's vapor pressure. That's a backwards one. Which of these compounds has the largest vapor pressure? Okay, so let's ask ourselves a question first. Does the largest vapor pressure have very big intermolecular forces or very small intermolecular forces? Right, it's going to be small. Yes. Right. So a big vapor pressure means that the molecules really want to be in the gas phase. They want to be away from each other. Right. That means they're not very attracted to each other. So very small intermolecular forces. All right. So now that we've determined we're looking for something with small intermolecular forces, let's take a look at our compounds and decide which of these has the strongest intermolecular forces, which has weaker ones, and how we would decide among them. So look at all of them. Think about what kind of intermolecular forces they have, and maybe just put them in order. Okay, either from strongest to weakest or weakest to strongest, whatever makes sense for you. Do any of these have hydrogen bonding? No, not at all. None of them do. All right. Are any of them polar? Are any of these polar? That would be the next strongest kind of force. It's a trickier one, isn't it? All right. So let's remember what we said about things that are polar. They have to have polar bonds and they have to be arranged unsymmetrically. None of these compounds that we have here have polar bonds, right? They're all between either atoms that are the same, like between carbon and carbon, or they're between carbon and hydrogen. And we said that we're going to treat carbon-hydrogen bonds as if they're perfectly evenly shared, perfectly not polar, perfectly covalent. So none of these compounds have a polar bond in them. So it doesn't matter how they're arranged. If there's no polar bonds, it's going to be overall not a polar molecule. So these do not have dipole forces. All right, that's London dispersion forces. That's all we have left, right? The least or lowest kind of intermolecular force. All right, well, how are we going to decide between them? Which one of these is going to have the stronger London dispersion forces? How can we decide between A, B, and C? What's different about them? Yes, thank you, Aisha. Their shapes, right? Their shapes are different and their size is different. Okay, so remember there were two things that we were going to consider if London dispersion forces were our deciding factor. The first one was the size, right? The ones that are bigger right? The molecules that are bigger, they have more mass, if you will. They're going to have more electrons. They're going to have more London dispersion forces, more opportunities for those electrons to slosh around. So which of these is the biggest? Okay. So C definitely is not linear, but it's not the biggest. If you count the sizes of them, if you count how many carbons are in there, I think you'll see the first one is larger. It's got more mass to it. So A would be the largest one. B and C kind of look the same though, right? They do look the same. And we have to be careful we're not deceived by the actual size of the print there. C looks larger because it takes up more distance up and down, but side to side, it really doesn't take up any more distance at all. B and C are actually the same size, right? They're the same number of carbon atoms, the same number of hydrogen, everything's the same about them. They're just put together a little bit differently. Okay, so size was the first deciding factor. So A has got stronger forces than B and C. And shape, that's the other contributing factor, right? A shape that has more surface area, that's more exposed, is going to have larger London dispersion forces, right? It's got more area, more ways to interact with its neighbor. Versus a compound where everything's all kind of balled up in itself, right? If it's all tiny and squished together, then that's going to have less surface area. So if you think about it, like a ball is a sphere, so that's some nice round shape. That has the smallest amount of surface area for the same volume of material. So look at B and C. Look at their shapes, right? If one of them's long and skinny, it's going to have more surface area. And if one of them's all kind of balled up on itself, looks kind of like a pin cushion, it's going to have a smaller surface area. So given that aspect of them to think about, which of those two, B or C, is going to have larger intermolecular forces? All right. So look at B, all the carbons are in like a nice little long chain. That's kind of making a little snake-like arrangement of the molecules as it gets built. And look at C, there's a carbon in the middle and then there's 3 more stuck to it. And then the hydrogens are all attached to that. And it's definitely a more compact kind of a shape there. So C is more compact. It's going to have less surface area for the same size. It's the same size as compound B. So because B has more surface area, it's going to have larger intermolecular forces. Okay, but that's not what we were looking for, right? We were looking for the one that had the smallest intermolecular forces, because the smaller forces that hold the molecules together is going to lead to a very big vapor pressure. All right. So here the answer was C. Okay, so we really had to think through all of those intermolecular forces, and then we had to really dig down into London dispersion forces and how the size and then the shape affected the strength of those forces. Okay, so C here has the smallest London dispersion forces. Sorry about that. C has the smallest London dispersion forces, the weakest forces. So it's going to have the largest vapor pressure. Right? Which one of these is going to have the smallest vapor pressure? Oh my goodness. There you go. Thank you, Haley. I knew if I waited long enough, someone would help me out there. Yeah, A is, right? It's got the strongest forces. That's the one that wants to stay together the most. So it's going to have the lowest vapor pressure. Not as many molecules are going to be up in the gas phase, making making gas pressure, right? They're going to hang out together. Perfect. All right. Let's try another one here. Which of these compounds has the lowest viscosity? Right. So remember, viscosity is how thick or how resistant a liquid is to being poured. So viscosity is another one of those properties that's directly related to intermolecular forces. Okay, so the stronger the intermolecular forces, the stronger or the larger is going to be our viscosity. All right, so we're looking for low viscosity. Do we want big intermolecular forces or small intermolecular forces? Small, good. All right. So which of these has the smallest intermolecular forces? So they're going to be the one with the lowest viscosity. It's a lot to sort through. You got to look at the structure. You got to think about all those features we've talked about for the last 2 weeks and put it all together. It's like a 5-step dimensional analysis problem, only it's all about the structure this time. All right. So what kind of forces are in these, right? So C has a lot of carbons and hydrogens in it, right? Those are all non-polar. Does it have hydrogen bonding? No, it doesn't. Hydrogen bonding requires hydrogen to be attached to the oxygen. That's not the case here. We do have a polar bond though. The carbon-oxygen bond is a polar bond. The electrons spend more time near the electronegative oxygen. And there's nothing to balance it, right? All the other bonds are non-polar. So C is a polar molecule. It has dipole forces. A and B don't. A and B are only London dispersion forces. Okay? And if we're looking for low viscosity, we want the lowest forces. So it can't be that one. It can't be C, right? That's the one with the highest, right? Right? You can see if you've picked C, right? You've thought about the question and got so excited about viscosity, you went to whatever you're thinking about, which might be the biggest when the question asks the smallest. So be careful. So just when how we had to be careful with the periodic trends, whether we were looking for the biggest size or the most metallic or the largest ionization energy, make sure you're reading the question carefully. Right, so the highest viscosity would be that dipole one, right? The lowest viscosity then, oh my goodness, we have a 50-50 shot here. All right, it's going to be A, right? Both of those have the smaller London dispersion forces. So the only difference between them is their size, right? So B is bigger. It's going to have stronger London dispersion forces. So it will have a larger viscosity. So A is the one, right? We were looking for the small one, right? For the low viscosity, right? We could have put them in order, right? If we were so inclined. This question just wanted to know which was the biggest or the smallest. All right. We good with that? Any other questions on that before we move on? All right. There is one more. I forgot. There was one more question. All right. We'll practice reading graphs. That's going to be a skill for the second half of our class today. What is the boiling point of ethanol? Okay, so ethanol is the second line here. It's this one here, the red one there, and right before water. What is the boiling point of ethanol at the top of Denali, where the atmospheric pressure is 330 torr? So what is the boiling point of ethanol? right? So remember, things boil when the vapor pressure equals the atmospheric pressure. That's when we say things are boiling. They're changing from liquid to gas. Well, what do we think? Okay. Right. So we're going to go to, right, atmospheric pressure is 330 torr. So we're going to find on our axis that shows vapor pressure where 330 torr is. Okay. And then we're going to go straight across to that vapor pressure line, right? Because when the vapor pressure equals 330 torr, then ethanol will boil under those conditions, right? And that happens around 60 degrees. It does. All right. Okay. It's just another way to get that same information, right? Without using words, we can use a graph. And that'll come into play again right near the end of our time today. All right. Okay, so let's take a look a little more at vapor pressure. So we saw, right, let me go back one. So we saw from this graph that vapor pressure and temperature don't have a linear relationship, right? Vapor pressure increases when temperature increases, but it's not going in a straight line. And vapor pressure is notoriously difficult to measure. You need some special equipment and things. It's just kind of a pain in the butt to do. So we can model this though. We can take some data, a bunch of different vapor pressures, and make a graph that is a straight line. That's always easier to work with for us, easier to model. So if we graph on the y-axis, instead of vapor pressure, and we make a graph of natural log of vapor pressure. So that's a different function than we've used before. So make sure you've got your calculator near you. You can find the natural log button on your calculator because we're going to do some math with that. So have that nearby. But if we plot natural log of vapor pressure as a function of not temperature, but 1 over the temperature, 1 divided by the temperature, we do get pretty close to a straight line. And that's nice because we know how to work with straight lines. We can put them in Excel. We can use the equation of a line and solve all kinds of problems. And the slope of that line is equal to, it's a negative slope, right? So it's equal to the opposite of the heat of vaporization. So that's delta H, the enthalpy change for vaporizing, for going from the liquid to the gas in terms of energy per mole, divided by R. Right? That is our same R from before. I told you it was going to keep coming up. Here it is. What's different about it is it's using energy, more familiar energy units. It's using energy units of joules per mole Kelvin. So it's the same R, but it's got a different number because it has a different unit. So we're going to use these units here in this part of our course. So R is 8.314 joules per mole Kelvin. All right, so here's how that equation looks, right? So if you're not sure, like, how is that looking like a straight line? Oops. Right. Here is that equation. It's the Clausius-Clapeyron equation. So again, 2 guys couldn't decide who to name it after, so they both got credit. So the y is the natural log of P, right? So that's our y variable. Our x variable was 1 over temperature, right? Our slope is the m. So that's the negative heat of vaporization divided by R. And then there's a y-intercept. That's the b, right? In our equation of a line, there's always a b. And it's natural log of something, natural log of some number. And that really doesn't have any physical meaning. And that's not really helpful, right? So usually it's more helpful to have a slightly different form of this equation, because usually we only know 1 or 2 points on this line. So a more useful form is the one that's written over here. It's called the 2-point version because it requires you to know two data points, right? You have to know one set of temperature and pressure, vapor pressure, that goes together, and a second set of temperature and vapor pressure data. So instead of having the whole line, it's going to use those 2 points to create that whole line there. So there's 6 different variables in that equation. Okay, you find them all. There's 6. You should be able to solve for any one of those 6, right? And that looks complicated right now. So we're going to do an example in a lot of detail to kind of work our way through there. How to solve it numerically using our calculator, and how to, kind of manipulate things around to do the algebra. If this is an unfamiliar idea, or you've been a long time since you've done natural logs, this would be something to get yourself into the Science Learning Center real quick and work with some of those tutors on straightening that out. I'm of course happy to help you too, but I would not delay. Don't wait for me. Get the help as soon as you can by stopping in there. They're open tomorrow for sure. So we'll take a look when we do the sample problem, how to keep track of all the minus signs and the units, and we'll talk about all that. And we'll talk about how to use your calculator for the natural log function. Okay, so hopefully you've got your calculators with you, because that math is coming up right about now. Now is the time for that math problem. So we'll take a look at how do you know when to use this equation, and then how to actually utilize the equation. How are we going to put numbers in there and make it work? Okay, so here's our question. A substance has a heat of vaporization. Okay, so remember, that's delta H for the vaporization process. That's what that means, a heat of vaporization. It's an enthalpy change for that process of 16.69 kilojoules per mole. At 254.3 Kelvin, it has a vapor pressure of 92.44 millimeters of mercury. Calculate the vapor pressure at a different temperature at 275.7 Kelvin. All right. How do we even know what to do with this information, right? So it's going on and on about vapor pressure here. And you can see that there's 2 different temperatures, right? So you have a set of data. You know that 254.3 Kelvin goes with, right? It's a data pair. That's a temperature. And the vapor pressure that goes with that at that temperature is 92.44 millimeters of mercury. That's one data point. You want to calculate the vapor pressure at a different data point, right? At a different temperature. So right away, you should be thinking, I'm talking about vapor pressure. I have 2 data points. I probably need to use that 2-point version of the Clausius-Clapeyron equation. I probably need to use that equation over there in the box. Okay. I'm going to warn you now that there is lots of different ways to write that equation. So if you're Googling it or looking it up online or watching videos, you may see slightly different versions of it because they've done a little algebra manipulation. So even though it might look the same, watch out for where the 1s and the 2s are, because by moving those around, you can change the signs of things, and be careful what units they're talking about. So when you kind of go out there and are looking for more information or examples, be careful that you're looking at those equations and realizing what the different variables are representing, right? I like this version we have because it keeps the 2s and the 1s consistent. So the 2 is always first. So it's kind of like final minus initial. So the 2 is always first. So pressure 2 is on top, pressure 1 is on the bottom. Temperature 2 is first, and then we subtract 1 over temperature 1. It does have a minus sign out front, and I know that's disturbing, but we'll just be careful and we'll keep track of that. Okay, but just realize other versions might look a little bit different because they've manipulated that equation and have it in a slightly different algebra form. Okay, so we know we're going to use that equation. All right, so there it is, right, in the form that I like it in. So that's why it's there, right? The next step is probably just let's organize ourselves. So if you remember when we did gas laws, right? And we had algebra equations to solve. We just kind of organized ourselves and figured out what data do we have? What data are we, what are we trying to calculate? Are the units all correct? Like, let's just kind of list what we know, and then we'll put it all together. Okay. So what we know is a set of data between 254.3 Kelvin. We know it goes with the vapor pressure of 92.44 millimeters of mercury. You can call that condition 1, you can call it condition 2, it doesn't matter. As long as those two stay together, we're going to be in good shape. Personally, I like to make the thing that I'm looking for to be pressure 2. It's much easier to solve things algebraically without making a mistake if you put your unknown, the thing you're solving for, in the numerator, in the top. When the thing you're looking for is in the bottom, the algebra just always seems to go wrong. So I will advise you to do the same. Right? You don't have to, as long as you're keeping track of things and doing the algebra correctly, we will get exactly the same answer. Right? The odds are, though, if your variable is in the bottom, in the denominator, the odds are the algebra is going to go bad. So I have it so that pressure 2 is what we're looking for. That's in the numerator there in the natural log term. And my temperature 2 is 275.7 Kelvin. Temperature has to be in Kelvin here. Again, we're talking, it's not a gas law, but it is related to gases. So Kelvin is our unit of temperature. It's in the value of R that we're using. It uses units of Kelvin. Okay, so we have to could be converting if we have Celsius information into Kelvin. All right. The other thing to note is that the heat of vaporization, the delta H there, that typically is in units of kilojoules per mole. R, the value of R that we have, is in units of joules per mole Kelvin. Right? Those two don't match right now. They need to match, right? So the units that we're using for energy in the heat of vaporization have to match the energy units in R. Okay? They don't have to be anything in particular, but they do need to be the same. I chose, when I put that value in, right, I chose to change my kilojoules into joules. Okay. You could change the joules into kilojoules. You'll just be then converting your R value into different units. Again, we will get exactly the same answer. Right? It just, as long as we're both doing our algebra correctly, we're going to be fine. All right. The other thing I'm going to point out is the units for pressure. So again, we're doing a ratio of our pressures. So it doesn't matter at all what unit your pressure is in, as long as they're the same, right? They just have to be the same unit of pressure. They don't have to be in atmospheres. They don't have to be in torr. They can be in whatever pressure units your little heart desires, right? But they just have to be the same. That's the only thing that has to happen. And because it's not specified in this problem, I'm going to do what every lazy chemist does. And I'm just going to leave the units in whatever they are, right? It didn't tell me what units my pressure had to be in. So I'm just going to leave it in millimeters of mercury, right? As weird as that unit is, there's no need to change it. All right. So far, so good. Are we hanging in there with this math? All right. So on the right side, if you look on the right side, everything there is just a number, right? There's some units, right? All those units are actually going to end up canceling, right? Those units of kilojoules are going to cancel. The units of joules are going to cancel. The units of moles are going to cancel. And the units of Kelvin are going to cancel. On the right side, all of those numbers and units are going to boil down just to be a number. Okay, so you can put that in your calculator, okay, and come up with just a number for that right side of the equal sign. Right now, we've got to be careful, right? Because you have to do what's in parentheses, right? You're going to do what's in parentheses first. So make sure when you're entering that in your calculator, right, you're entering in some parentheses in the right places. So I'm going to show you the result of just doing the math on the right side. Okay, so I want you to make sure you can check that you get that right numerical value. Okay. All right, so I haven't done anything to the left side, so I'm just going to leave it there. Natural log of P2 divided by 92.44 millimeters of mercury. I'm just going to leave that alone. And that equals the result of everything on the right side. You'll note there's, again, all the units are gone. It's just a number. Okay. If you can give me a thumbs up if you were able to get that number, be great. All right. Terrific. All right. Okay, good. Right. So, it's been a while since we've used our calculators. We've been drawing pictures for a long time. All right. So we've got our calculators working again. Okay. Now here's the problem. Right. Now we have to do something about this natural log function. Right. Because this on the left side, it's the natural log of that ratio between the two pressures. And we want to know what one of the pressures is. So we need to make that natural log function go away. Right? It's a math function. So the way we do that is we do the opposite math function. It's inverse function. So on your calculator, right, if you can locate the natural log button, probably right above it, it's probably a function you have to shift to. It should say something like e to the x. Right, have we found that? That e to the x is the opposite of the natural log function. So that's how we're going to undo this natural log function. We're going to do that inverse function, that e to the x function on both sides, right? So if your calculator's sitting there holding your number, 0.6127, right? You can use your shift, right, and get to that inverse function. So you want to push that e to the x button. That is the opposite of the natural log function. So when you do that on both sides, the natural log function is going to go away, right? And you're going to now have a different number, right? So you're going to have the natural log function's gone, but that proportion is still there. It's still P2 over 92.44 millimeters of mercury. And now it equals a different number, right? Because you did the e to the x function on 0.6127. All right. So try that out. Okay. If you can give me a thumbs up if you got that to work properly. All right. Okay. And again, if you can't, or if you didn't, or you're not sure, right? This is, again, something to scoot over again to the Science Learning Center or catch me somewhere in the hallway, but let's not wait too long, right? Don't wait for me. Let's get help right away. Because this is exactly the kind of math function that you're going to be seeing next semester in Chem 132. It seems like every single one of the math relationships in that chapter looks kind of like this. It's got a natural log, it's got parentheses, it's got upside down temperatures. It's just kind of a mess. So yeah, so let's be careful there. All right. Now we need to solve for pressure too. We're not done yet, right? Hopefully now it's a little easier to see how we solve for the pressure too, right? We multiply both sides by that number that's in the denominator underneath pressure 2, multiply both sides by 92.44 and the unit, millimeters of mercury. Right? When we multiply both sides by that, now we're going to end up with a unit finally. Okay, and we're going to end up with 170.6 millimeters of mercury. Okay, how do we do with that? So after a scary math problem like this, I like to ask myself, does that even make sense? Is that really what I was expecting? Right, so let's kind of go back to the problem. And we have a temperature of 254.3 Kelvin and a certain vapor pressure, 92.44 millimeters of mercury. And the temperature is now bigger. It's 275.7 Kelvin. So since the temperature went up, did we expect the vapor pressure to go up as well? Do we need to reevaluate our math? Okay, so if the temperature goes up, right, we're adding average kinetic energy to our molecules. They're moving more. Are they going to be more likely to stay together in the liquid phase or run around in the gas phase? If they've got a little more energy there. So if they've got more temperature, more average kinetic energy, more of the molecules are going to be moving around, more of them are going to be in the gas phase, and that means the vapor pressure is going to be bigger, right? We would expect to have more gas, right? So the fact that we calculated a vapor pressure at this higher temperature to be bigger than the original vapor pressure, we say, yeah, that kind of makes sense, right? I feel like that makes sense. So we can kind of, have a little more confidence in our mathematical result there. Okay, these are going to take some practice, right? This is some math that we haven't dealt with at all this semester, and it's probably been a while since we've had any reason to do natural log functions. And even if you were using them in calculus, you were using them in a completely different way. So definitely practice with this. I'm going to give you a warning now about our discussion group activity coming up. There's a question like this on there, so that won't be a surprise, I think. But what I do want to remind you of is that, again, remember, vapor pressure is really a challenge to measure. So often we don't have data the way this problem presents it. Often we don't know a vapor pressure and temperature combination, but there is something we can measure really, really easily, and that's boiling point, right? If we can measure the temperature at which something boils normally, meaning at 1 atmosphere. So again, let's think about what boiling means. It means the vapor pressure equals the outside atmosphere. So the normal boiling temperature, the normal boiling point, is the temperature when the vapor pressure equals 1 atm, 1 atmosphere by definition. All right. So if you're given the normal boiling point, you are really given a vapor pressure and temperature combination. Right? It just doesn't look like it the way it looks like it in this problem. So you might want to write that down. You might need that information later, right? So somebody write that down. So when you're working on your group activity, at least one of you has that information there. All right. Okay. All right. Questions on that one before we move to the other few other properties to talk about. Okay. All right. Make sure I'm checking all my places to check here. All right. Well, then I guess let's look at a few other properties. We're not going to, talk about them as deeply because I think we already know what some of them are. All right. So we've talked about all the ones that are white there. We're going to talk about these orange ones here that just got filled in orange. Melting point, right? That's the melting temperature. What temperature do things melt at? Delta H fusion, that's the enthalpy change for the melting process for going from a solid to a liquid. Delta H of vaporization, we just kind of saw with the vapor pressure, it's the enthalpy change. Okay? Delta H for the vaporization process, going from liquid to gas. And the boiling point, which we've mentioned a few times now. Okay? And what temperature do we have to get to for those molecules to all leave the liquid phase? All right. All of those, remember all the ones that are circled in blue, Those all get larger when the intermolecular forces get larger. Vapor pressure is the only one that's backwards there. All right. So for the visual among us, right? Right, sometimes the big arrows are just helpful, right? So when intermolecular forces, that's IMF, when those get larger, almost all the properties get larger. Surface tension, viscosity, capillary action, right? Adhesion and cohesion, right? We didn't mention them specifically here. And all those new ones, melting point, boiling point, heat of fusion, heat of vaporization, those all increase when the forces get stronger, right? Those all take more energy when those molecules are being held more tightly together. Vapor pressure is the opposite. The more tightly they're held, the smaller the vapor pressure. Right? Vapor pressure depends on the molecules being away from each other, not liking each other. So that requires low intermolecular forces. All right, so let's practice that. So let's, hopefully you've located the chat box by now, right? Or you can just yell out answers. That works too. That's fine too. All right, we'll use some of the same compounds we've used before, so we don't have to stop and redraw Lewis structures here. Which of these compounds has the lowest melting point? So lowest melting point. Does that mean big forces or small forces? Mm-hmm. Good. Good. Yeah. So it is B, right? So remember, we talked about all the forces in these ones, right? So pH 3 has the lowest of the kinds of intermolecular forces here, right? And we were looking for a low melting point. So we want the one with the lowest intermolecular forces, right? Which one would have the strongest or the highest melting point? It's gonna be A, right? The one with the strongest forces, right? So like I said, we could ask you to put them in order, right? Just kind of rank them based on their forces. Here we were just asking though, what's the absolute lowest or biggest in those cases? All right. Oh, we're back to our carbons again. Which of these compounds has the largest heat of vaporization, right? So we have to know a lot of vocabulary to answer that question. Largest heat of vaporization. Okay, so ask yourself, do I need a lot of intermolecular forces or a little bit? And then think about the intermolecular forces that are in these three compounds. These were the tricky ones where we had to really think down into the London dispersion forces. All right, yes, these all only have London dispersion forces. So right, now we've got to look at those secondary characteristics of size and then surface area, right? So size we should consider first. That's more important. And then surface area is important when we have two things that are the same size. So if we want a large heat of vaporization, we want the largest forces. So these all only have London dispersion. We have to look for the one with the biggest size, right? That top one was the bigger size. Of those other two, B then would have the next strongest forces. So it would have the next largest heat of vaporization, and then C would be the smallest. All right. Which of these compounds has the lowest heat of fusion? Okay. So maybe on the test, we're underlining some keywords like lowest, right? What does that mean to have a low heat of fusion? That means we have low intermolecular forces. Now you got to look at some structures. Now you've got to make some decisions. Which one has the smallest forces? That's the one with the smallest heat of fusion. Okay, we picked one out yet? Right, it is A. That one is the smallest in size of our two with only London dispersion forces. Right, our bottom one has dipole forces. That's a pretty strong intermolecular force compared to the other two. It's actually gonna have a much higher heat of fusion, that last one. Okay, so we're looking for the smallest one with London dispersion forces. That's our top one, A. All right. Questions on that? All right, how about boiling point? Which of these compounds has the highest or largest boiling point? Right? Okay. Here's the same three from the last slide. Okay. All right, if you want the highest boiling point, do you want the biggest intermolecular forces or the smaller intermolecular forces? Yeah. Want bigger forces. Okay. So these ones didn't all have just London dispersion, right? Remember that the bottom one has dipole forces. So it's, well, it is actually bigger than any of the other ones, but it has definitely a polar feature to it. So that's a stronger intermolecular force, right? So that's going to have the strongest intermolecular force. It'll have the highest boiling point, right? And then after that, will be the second one, and then the third, then the first one. A would have the weakest intermolecular forces, so it would have the lowest boiling point. All right. Wait, did that stir up any questions? Okay. All right. This is probably a great place to take a little tiny bit of a break, right? And stretch our legs a little bit. So what I'm going to do is I'm going to stop recording here, and then we'll start the recording again. So we'll end up with 2 recordings for our friends who can't be with us here. There we go. Well, welcome back. All right. So the second half of our class today it's a lot about graphs. It's a lot about visually representing a lot of the data and a lot of the information and the concepts that we've been working with. Right. So we'll start with changes of matter, right? Changes in states of matter, which is oddly enough where we started things on our very first day of class, right? We still have not left that first day of class. So a heating curve is one way of representing a lot of that data about when do things melt, how much energy does it take to melt them, all of those kind of properties we've just been talking about and relating to intermolecular forces. We can relate them to different phases of matter, and we can visualize that on a graph, right? We know a picture is often worth 1,000 words. So these graphs are just ways of collecting a lot of information and presenting it in a visual kind of way. So let's look at what these heating curves are. It's kind of, again, we're not creative in chemistry, so it's pretty much what it sounds like. It's a plot or a graph, a line, that's the curve part, of what happens when we heat something. So we're going to add heat to a material. So the x-axis is the amount of heat that's been added. Okay, so that's going to be on our x-axis. On our y-axis is the temperature, right? We kind of know what happens when we add heat to a material, right? As we're adding this heat energy, it's often used to raise the temperature of that material, right? So when we add heat, well, that material gets hotter. Like that's not a mystery to us. That seems to happen. We've played with that back in chapter 7 when we were looking at quantities of heat and how heat was related to a reaction. So that's not a mystery, right? But let's look at what is maybe something we didn't think about before. So if we start right at the beginning of this curve, right over here at the corner of the blue where it says solid, if we start down there at that curve and just add heat, right? So we know the temperature is going to get larger and larger and larger as we add heat until we get to some point, and then we add heat, but the temperature doesn't go up. And we're thinking, well, that's kind of a mystery. That's not expected, right? If I'm adding heat, shouldn't it just be getting hotter? And the answer is sort of, right? So that material is no longer using that heat to increase its average kinetic energy. It's now using that heat to do a phase change, right? So if you'll note on that graph, that's where that temperature is where it changes from a solid to a liquid, right? That's what's going on there. At that point, all the energy you're adding, all that heat you're dumping into that material isn't being used to increase the average kinetic energy. It's being used to break the intermolecular forces that are holding those molecules to each other in the solid phase and turning that material now into a liquid, right? So no temperature is changing, right? Our material isn't gaining any average kinetic energy. It's gaining heat, but it's using it to do not really a reaction, but a process. It's using that energy to break the intermolecular forces, right? And when it's done, right, when all that solid's been turned into a liquid, right, now we can go back to adding heat, and that added heat is going to increase the temperature of our liquid now. It's going to increase, right? But not forever, right? Because at some point that liquid is going to turn into a gas, right? At the boiling point, whatever the boiling temperature is for that material, right? And then at that point, when we add more heat, we add more energy. That energy doesn't go into raising the temperature. It doesn't go into kinetic energy. It goes into breaking the intermolecular forces that we've been talking about that hold the liquid molecules to each other. It breaks those intermolecular forces and turns our liquid into, well, the next phase, which is a gas phase. Okay. And then again, at that point, then we can add more heat and the temperature of our gas will increase. Okay. All of those things are things we've talked about before, right? Heating materials and having the temperature go up, different phase changes. We've talked about that. We've even talked about how much energy it takes to change from a solid to a gas, or well, we did from a solid to a gas in the Born-Haber cycle. We've done other things going from liquid to gas, liquid to gas when we boil things. Right? But that's kind of a new feature. That feature of the temperature not changing when we do a phase change, that might not be something we've ever thought about, right? Or really understood. But that's why you can have a glass of ice and water at the same time. You can have both of them there, right? So at that freezing point or that melting point, right, at that temperature, both the solid or the liquid could exist, right? And what's going on is that process, right, where the temperature isn't changing. We're right at that melting point temperature. So both the liquid and the solid can exist at the same time. Okay. All right, so no temperature change during a phase change. On your problem set for this weekend, you're going to have just a random sort of sample heating curve, kind of like the one over there on the right, and you'll be asked to figure out some data from just looking at that graph. So you should be able to figure out what the melting point and the boiling point are, right? Can you figure that out for this one? What's the melting point? Melting temperature, right? That's another word for it, melting point or melting temperature. It's going to be 0. It's where it flattens out in between the solid and the liquid. How about the boiling point? Yeah, Yeah, there you go. Right, it's where it flattens out between the liquid and the gas, right? So if you had a graph like this, you're getting that information, right? The length of that curve, how long that line is, tells you about delta H for either freezing or melting, and delta H for the vaporization process, right? It takes more energy, right, or a longer line typically to vaporize than it does to melt, right? You're doing a better job of separating things when you go to the gas phase, right? The slope of that line tells you how easy it is to change the temperature of the solid, the liquid, or the gas, right? And it's a little hard to tell from this drawing, but all those lines are different, right? All of those materials, whether it's a solid, a liquid, or a gas, has a different heat capacity, a different ability to change temperature when we add heat. Okay, so all of that data is in there somewhere, right? These are all processes we've talked about before. Okay, so I want to look at that graph over there on the right and just think about how we could quantify, right? That's measure, calculate, right? There's a number involved here. How we could quantify the amount of heat on each of these different parts of our graph. So say between A and B, right? So if you were going from A, right? A is right at the origin of our graph. Okay. If you were going from A to B, what's the equation? What's the relationship that tells you how heat is related to temperature change in particular? Do we remember that relationship? We've used it a ton of times, mostly in chapter 7. Yeah, there we go, right? So yeah. So between A and B, we're just heating up the solid, right? We had an equation that was used just for when things got hot and cold, right? That's exactly what's going on here. Our solid is getting hotter as we go from A to B, right? So Q, right? Remember Q is heat. Q is heat. It's an energy, right? It's going to have units of joules, equals the mass times the specific heat of that material, right? So we have to be careful that we get the heat capacity for the solid version of that material, because between A and B, that material is a solid, right? Times the temperature change. So whatever the temperature change is between A and B, that's what we're going to use there. All right. Now, trickier question. Between B and C, right? Think about what process is going on there. Between B and C, we're melting. So how are we going to quantify the heat for the melting process? That's more like almost like, again, it's not really a chemical reaction, but it's a physical change, right? It's kind of like a reaction. It's a process as opposed to a reaction. So between B and C, we're melting. We're doing a phase change. The temperature isn't changing, right? It's a flat line, right? So we can't use that first. Yeah, we can't use that first relationship, but we can use the heat of fusion. Now remember that delta H is always energy per mole, right? So it depends on how many moles we have. So that's what that N is there. So N is our little symbol for moles, right? So the heat in this particular process depends on how many moles of the material we're talking about here, times delta H for the fusion, right? So that, again, remember the heat of fusion it's the enthalpy change for melting or freezing, right? If we're going in the other direction, melting. And that has units of energy per mole. So we're going to multiply by how many moles we do have, and then we'll have just energy units. We've done that before, right? We've used delta H in reactions and processes to figure out how amounts of energy are related to moles of things in a reaction, right? We've done all that, right? So this is, again, right, the same idea, but in a slightly different context. So we're naturally reviewing, right? Here as we're getting close to the end. That's always nice. Okay, what's going on between C and D? The temperature is back to changing again, right? We're heating again. what are we heating? Okay, now we're heating the liquid. Okay, so the equation we're going to use is going to look kind of like the first one again, but instead of heating the solid, we're heating the liquid. So our heat capacity, our specific heat, has to be for the liquid, right? So again, when we look these up, right, if we're looking at data tables or, reading a problem, we need to make sure we get the right information in the right place, right? Times the temperature change for the liquid. So that would be the temperature change between C and D, right? Always the final minus the initial. Okay, so it'd be the temperature at D minus the temperature at C. All right, what's going on between D and E? Well, it's flat again, right? So we're not heating anything. What are we doing? Yeah, we're boiling it. We're vaporizing it, right? So we're turning things from a liquid into a gas. So what do you think we need to know here? What's our proper of information that we need? What equation are we going to use? Okay. All right. Well, for vaporizing, it's a change. It's a process, just like we did for melting. We're going to need to know what delta H is for that process, right? So that's the heat of vaporization. So delta H for vaporizing, for turning it into a gas from a liquid, right? Again, that's energy per mole. So we need to know how many moles. That's the N there out at the front. Okay. So all of these are for calculating the amounts of heat or the amount of energy for these different kinds of things we're doing, right? We're heating, then we're melting, we're heating, and then we're boiling. And then what are we doing between E and F? We are certainly back to the heating again, right? You can see the temperature is changing between E and F, okay? Except now we have a gas, right? So we have to use the heat capacity for the gas, right? And the temperature change for the gas, right? All of these have to be for that material that we're talking about here. So we've got these different regions of the heating curve. And depending on where we start, we are going to be able to calculate or determine how much heat is happening to get from one point to the other, right? So to have a certain change take place. So the best way to do this is probably to just jump right in. Let's look at an example with actual numbers, right? So far we've been talking about it sort of in the abstract. We don't have any actual numbers on any of our graphs here. So the next slide is one of your handouts. So if you've got that, I think it's your last handout in the packet. It has all this data on it. Okay. If not, you might want to take a screenshot of it so you have that data there to work with. So you have a heating curve over there. It has data on it, right? It has some values for the different temperatures. Okay. It has some different regions of the curve labeled. So this one doesn't label the points, it just labels the regions. So A is that first slopey area, B is the flat area, C is the second slopey area, D is the second flat line there, and then E is another sloping area there. So different things are happening in those different regions. So you should probably be able to tell me what's going on in each of those regions. But you've also got all this data over on the side here. Oh my goodness. A lot of data, right? Because we have a lot of different materials with a lot of different properties, right? So we need to know all those different things. I even gave you the molar mass just for fun. So let's look at the question and see how it relates to what we've been talking about. How much energy is required to heat 45 grams of solid benzene? So the formula of that is C6H6 from 0.0 degrees Celsius all the way up to benzene vapor at 100.0 degrees Celsius. Okay, so our graph does start at 0. The temperature at the bottom is 0 degrees Celsius. All right, so you want to heat that material from 0 up to 100. And you can see that in order to get from 0 to 100, it's going to pass through a couple of different phases. So we're going to need to account for that, right? We're going to have to account for what's happening in region A. That's different from what's happening in region B or C or D or E, right? We have different relationships based on what process is happening. We had one equation for when things were changing their temperature and another equation when it was changing phase. Okay? So what I want to do is pause here, give you a good 5 to 10 minutes to work through this problem, see if you can come up with a numerical value. Let's just see how far you get in like 5 or 10 minutes. And then what I'm going to do, I'll reconvene here. I'm not going anywhere. I'll be right here. But I'm going to pause the recording again, just for a little bit here. All right, so we're ready to take a look at our results now. Right, so let's see how you did. All right, so for the first part, right, let's see how you did there. Did you use the right relationship? Right? Did you look at what was going on for just the solid? So you had to get the right heat capacity for the solid, right? So not the one for the liquid, not the one for the gas. You had to select the right one. And then the temperature change, right? That's a tricky one. So remember the solid, right? Once you got to 5.5 degrees, it wasn't going to be a solid anymore. It was going to start to melt. So the temperature change for the solid is the final minus the initial. Well, the highest temperature the solid can get to is 5.5 degrees Celsius, right? So minus 0.0. And the units are going to be joules here for our Q equals MC delta T relationship. All right, were you able to get that? Give a little thumbs up if you were able to get that one. Good. Awesome. All right. So the second one was going to be probably a little bit trickier, right? Because that one involved a process or a reaction. So in this one, we needed moles. Did you remember to change from grams into moles? Right. So we had the molar mass there. I did give it to you. That was kind of me. So you could find the moles first, and then you have to use the right delta H value. It's a delta H for fusion here. It's the smaller one, 9.9 kilojoules for every 1 mole. All right, so you should have gotten about 5.7 kilojoules. So again, it's still an energy unit, but you'll notice a different energy unit. That's going to be an issue when we go to add these all together. We're going to have to be mindful of the units when we add them together. They all have to be the same unit or we can't add them together. All right, let's take the third one, right? That's when we were going to be heating the liquid. Okay, so we're back to the mass, so the 45 grams. It's the same sample, right? We heated it from beginning to end. Mass is conserved, right? We haven't lost any mass along the way. So 45 grams is still our mass. Did you get the heat capacity for the liquid version? All right, and then the temperature change was a tricky one, right? It's only a liquid between 5.5 degrees Celsius and 80.1 degrees Celsius. Any more or less than that, and it's either a gas or a solid. Right, so the temperature change for the liquid that the liquid goes through, it goes through the whole temperature change from just melted up to not quite boiled, 80.1 degrees minus 5.5 degrees. Okay, so that took quite a bit of energy, 5,800 joules. Okay. Then we're going to boil, right? So we're going to need not the heat of fusion, but the heat of vaporization. So that's usually the bigger value. Right, and again, we need to be in moles, right? So 45 grams need to be changed into moles, right? And times the delta H of vaporization, the enthalpy change for the boiling process. And we get 18 kilojoules there. All right. And then the last step was to finish heating that benzene, right? It's at 80.1 degrees as it's being turned from a liquid into a gas, but we want it all the way up to 100 degrees Celsius. So we need to apply a little heat to the gas as well, right? So it's the same form of the equation as in the first one and the third one, but we're going to have to use the heat capacity for the gas here and the temperature change that the gas is going to go through. It's going to change from 80.1 degrees Celsius to 100.0 degrees Celsius. And that's going to take more energy. It's going to take 1200 joules. We still haven't answered the question, right? We're exhausted and we haven't answered the question yet. How much energy does it take to do all of this, right? We need to add these all together, right? And again, we can't add them together if they all have different units. So we need to make a decision. We need to change them all into the same unit. So you can change them all into kilojoules. You can change them all into joules. You can change them all into kilowatt hours if you want to. We're going to probably do the lazy thing, right? And just change one of them into different units. I changed them all into kilojoules. That's just a comfortable unit of energy that we've been using all semester. So I'm going to change the units into kilojoules and then add everything together. And I will get 31 kilojoules, right? So if you were able to get to the end of that problem, how did you do? Did you get close to that, or at least within, rounding errors? So it probably took a little while to do some of those calculations. It's been a long time since we thought about these things. I think we learned about those back in early October. That was part of chapter 7. So again, you can see how we're reviewing and we're bringing together all of the ideas from the whole semester, again, in just a slightly different context. Here we were looking at things boiling or melting in terms of overcoming those intermolecular forces, right? So we got to revisit some of those old ideas again, and we can remind ourselves how to do things quantitatively. And that's what's going to happen on your problem set. You're going to have, I'll go back one, right? You're going to have just a generic kind of curve there, and you're going to be asked to identify what's going on with it, right? What's going on in the different regions of the curve? Can you figure out what the melting point and boiling point are from the data on there? And then can you do a calculation kind of like we did, right? Can you figure out how much energy it takes to get from some point on the graph to a different point on the graph? Okay. Now, remember in our example that we did, we started at the bottom of the curve, right? We started at the origin of our graph right down here. You don't have to, right? And in fact, you probably aren't going to on your problem set, right? You might start in the middle, right? What if you started at 60 degrees Celsius and we're going up to 100? Well, you would go through some different processes. You wouldn't go through all the processes that we did in our problem. If we started at 60, we'd only have to heat our liquid a little bit from 60 to 80.1 degrees, and then we'd boil it, and then we'd heat the gas, right? We wouldn't have to do all the stuff that comes before it. Okay, so just kind of be aware of where you are on that heating curve, right? That'll kind of help you decide what processes are going to happen to get me from where I'm asked to start and where I'm asked to end, right? Make sure that you're answering the question that was put to you, that you follow that. All right, some questions on that. How are we feeling about that? Do we have anything that you need to be reminded of? If you want to look back at it in more detail, I'll just remind you again, it's chapter 7. We used a lot of this when we were talking about quantifying heat. And we also used it quite a bit in our calorimetry lab. That's where the other place that we would have seen this. All righty. Okay. So we're going to go back to a little more of a qualitative look at, again, how to kind of present this data. There's a lot of data going back to just how materials are, just even in what state they're in, right? So we're going to go back again, oddly enough, to the very first day of class. It seems like we're always doing that, right? And we're going to go back to solid, liquid, gas, right? We're going to look at a phase diagram. Okay, so this is one of my favorite graphs. It has color, it has labels, it reminds us of everything we've done, and then it has those nice pictures that give us that sense of what's going on at the molecular level, right? So if we think about the gas there, down there in the lower right, you can see that picture of it. We've got atoms or molecules, whatever they are, and they're pretty far apart and they're kind of minding their own business and they're not really interacting. So under what conditions is our material going to be in the gas phase? Well, it has to have enough energy, right? Enough average kinetic energy to overcome those intermolecular forces. We're probably going to want to be at a pretty big temperature, right? So at high temperatures, and we're going to want to be at a low pressure, right? We don't want to be squishing and compressing and pressing on our particles and moving them back close together, right? So in that bottom lower right corner, that's where the temperature is the highest, right? That's our x-axis. And our pressure is the lowest. Pressure is on the y-axis. So these kind of graphs are going to let us represent what's going on under different temperature and pressure combinations. So it's kind of important to know what phase of matter your material is going to be in if you want it to have certain properties, right? If you want it to use it as a container under a certain set of pressure and temperature conditions, it might be nice to know that it's going to stay a solid for that entire temperature range, right? You don't want it suddenly turning into a liquid in the middle of your experiment, and then all of your materials are lost. Okay, so this is why we use these phase diagrams. All we want you to be able to do is to read them, kind of look at them and understand what kind of information they're conveying to you. Okay, so all of these have kind of the same features, right? They've all got regions where there's a solid, a liquid, and a gas. So we've talked about the gas being where the temperature is large, lots of kinetic energy to overcome intermolecular forces, and the pressure is relatively small, right? We're not pushing those molecules close together so that they interact with each other. Well, let's go to the opposite extreme. Let's go to a very low temperature and a very high pressure. Okay, so we're going to go into the upper left corner of our graph here, right? And no surprise, right? When we slow the molecules down and don't let them have a lot of average kinetic energy, right? They're going to be able to basically give in to their attractions to each other, right? At high pressure, we're pushing them together, right? They're probably going to be a solid, right? At those higher pressures and lower temperatures. Okay, the liquid's the middle ground, right? At those intermediate temperatures and pressures, there's going to be a region where our material is a liquid. And there's going to be lines that separate these phases, right? There's a line between the solid and the liquid, right? When we cross that line, we're either melting when we're going from solid to liquid, or we're freezing when we're going from the liquid to the solid. If you're right on the line, then you have both the solid and the liquid present, right? So that's kind of like having your glass of ice water, right? You have ice and water at the same time. Okay, so the lines are the transitional lines where the phases are moving from one to another. Okay, what we've not seen before, what we really haven't thought about, we've thought a lot about changing from one phase to another. But what's new here is on a phase diagram, we see this notion of a triple point, right? So it's that point T right in the middle where the three lines come together. There it is. It's the weirdest thing. It really is. It's at that point where we have all three phases are present. All three, solid, liquid, and gas at the same time. Ice, water, and steam at the same time. I don't think we've ever seen that, right? That doesn't happen at a condition that is normal for us. It happens under some weird conditions. It's pretty close to 0 degrees for water, but the pressure is very low. I had to put a video of that on Blackboard for you, right? So you can take a look at that and see what it looks like to see ice and water and steam at the same time. is all in the same container, all in equilibrium. They would exist there, indefinitely if we maintain that condition. So that's a pretty weird situation to have all three phases present, but it happens at that very specific set of temperature and pressure conditions. The other condition that we really haven't talked about or seen is at the end of the line between liquid and gas, right? The other lines don't have an end. The line between liquid and gas has an end. There comes a point at a certain pressure and temperature where the distinction between liquid and gas is not so clear. And we say we have a different kind of material. It's called a supercritical fluid. So the end of the line is called the critical point. And once you go past that, you have this material that is really neither a liquid or not really a gas. It's a little bit of both. Again, that usually happens at exotic conditions, things we don't see here on Earth. So maybe somewhere in the atmosphere of Jupiter that happens. But there is one example I can think of that does happen at relatively reasonable conditions, and it's for carbon dioxide. Carbon dioxide becomes a supercritical fluid at conditions we can replicate easily in the lab. And that's one application of that is to use it to extract caffeine from coffee, to decaffeinate it. It's nice because it doesn't really leave behind any residue that is harmful to us, right? It's just carbon dioxide. So it can be used to remove the caffeine and leave the coffee bean alone without leaving behind some of the harsher chemicals that other methods of decaffeinating will do. So that's kind of a neat little application of it. It has a few others, but that one's kind of one that we might be the most familiar with. Okay. All right. So again, you should be able to look at that graph and read it and understand what's going on. So let's practice doing that real quick. All right, so here's bromine. All right, here's its phase diagram. It's different. It's got a little different shape. It's got some different different units and different scales on it. So can you label which regions are solid, liquid, or gas? Okay, you just give me a thumbs up that says, yeah, I can do that. All right, do you have a question, Majida? Or are you just saying you got it?
Just saying I've got it.
Okay, thank you. All right, perfect. All right, we could label those regions solid, liquid, or gas. Can you find the triple points? Oh, I bet you can. Good. Triple point, right? That's where all three lines intersect. All right, what state of matter is present at point A? So there's an A on the graph. Can you tell me whether that material is a solid, a liquid, or a gas under those conditions? Yeah, and that is a liquid. So A is right smack dab in the middle of the liquid section. So it's only a liquid. It's not transitioning between a liquid and a solid or a liquid and a gas. It's only a liquid. All right, what about point B? Point B is different. Point B is right on the line. So what states of matter would be present at B? Okay, what do we think? Well, it's right on the line, right? So what that means is, again, if we're right on the line, we're at that point where the liquid and the gas are both present, right? We're in that transition phase there where both materials could exist at that set of conditions. They can exist together in equilibrium. There'd be a balance between them. All right, how about point C? It's kind of down there near the origin. What materials are there? It's also on the line. Right. If it's on the line, right, it's on that solid gas line. So both the solid and the gas will be there. All right, now the big money question here. What's the boiling point? The boiling temperature at 330 torr. Okay. Right. So I'm going to remind you that boiling is when the vapor pressure equals the atmospheric pressure. And we want to know what's the temperature of boiling at 330 torr. Okay. We have a little bit of a problem, don't we? When we look at our scale on the pressure of the pressure units, that's not in torr. All those units and those numbers there are all for kilopascals. Right? That's a funny little unit of pressure that we haven't seen in a really long time. Right? So let's remember all the way back to chapter 6, which I think now completes our discussion of all the chapters. I think that's the only one we haven't talked about yet. Chapter 6, back to gases. We need to know how to change the units between torr and kilopascals. I've got that reminder up there in the green arrow, what that conversion factor is. All right. So what we want to do is convert our 330 torr into kilopascals, and then we'll read off the graph. Where do we change between a liquid and a gas when that is the pressure, right? So when we do that math, it's about, I don't know, like something around 45-ish, right? Is 45 kilopascals is about 330 torr, right? So we'll just go straight across and we'll see where that liquid and gas transition happens, right? And you can see it happens somewhere around, I don't know, 38, 39 degrees, somewhere in there. So we're just reading things off the graph, right? We didn't have to know anything, right? We could just use the information on the graph and think about how it's organized. All right, questions on that? All right, so again, you get a chance to practice a little bit of that on the problem set, as well as some of the assigned problems at the end of the chapter. I know we're over, but we have about 7 more minutes if you can hang in there. Is that okay with everybody? Well, if you're still here, I'm going to assume it's okay. All right. Okay. So the last thing was to take a look at this bizarre little molecule here, dihydrogen monoxide. All right. What is that? You probably know it by another name. That's its official name. Dihydrogen, 2 hydrogens, H2, monoxide, 1 oxygen. It's H2O, okay? It sounds scarier when you call it that. But water does some extremely unusual things. So we're going to look at both its phase diagram, now that we know what those are, and its heating curve, now that we know what those are. And then we're going to tie it all back to its structure, because that's what this chapter was all about, how the structure affects the properties. So water is has an unusual looking phase diagram. So if you look on the left there, you might not notice how it looks weird, right? It looks kind of the same, right? It has a solid gas in the liquid region in the middle. That doesn't look very different. But what is different about it is the line between the solid and the liquid. For most materials, and by most I mean like 99.999% of them, that line slopes in a positive direction. It slopes towards the right there. It leans to the right. This one leans to the left. Okay, and it's one of the very few materials that does this. And that has a consequence, right? So if you just pick a temperature, I don't know, something below 0, let's pick a temperature below 0. and just increase the temperature, or excuse me, increase the pressure. I'm sorry. So pick a temperature and increase the pressure. So let's just pick a spot right here. Let's just pick about 0. Let's pick 0 since there's a line there already. And we'll just increase the pressure. We'll just start pushing the molecules closer and closer and closer together, right? And normally what we would expect is that as the pressure goes up, we're more likely to form solid than a liquid, right? As we push those molecules closer and closer together, right? Well, what happens with water is at some point we press on it and we press on it and we go from the gas to the solid. And as we keep pressing, we then eventually end up with a liquid, right? So the more compressed it is, right, the more it's a liquid. That means the liquid version of a material of water is more dense than the solid version. That is not typical, right? For most things, when you make them into a solid, it's more dense. You've put the same amount of mass in a smaller volume, and that's more dense. And of course, the solid would sink in a pile of the liquid version. Okay. Here, that doesn't happen. Ice floats, right? We know that, we observe it all the time. We don't really think about it. But every other material, the solid will sink in its own liquid. It's more dense. And thank goodness it happens this way, right? Otherwise, if water were normal, like everything else, if water had a more dense solid, what would happen every time winter happened, right? The water on your lake would freeze and it would sink, right? And then it would freeze, right? And more of it would sink until eventually your whole lake was the solid chunk of frozen ice covered with a layer of dead frozen fish, right? There'd be no place for the fish to hang out all winter. They would just freeze and then die, right? But what happens is the water freezes and it floats. Right? Now you've got a layer over the surface, and that allows the water underneath to stay below freeze or above freezing, and the fish can hang out there all winter. Right? So it's a darn good thing that ice floats, right? It makes for life in the water and on Earth really to be possible, not to be melodramatic, but that's really, right, that's what makes it possible. The fact that solid ice is less dense than liquid ice. We're going to look at the structure and see why that is true. Right? The other strange thing that water does is over here on the heating curve, it has another unusual property, which again makes it ideal for us here on Earth. Right? It's just an amazing material that makes everything that we know of in the biologies possible. So what's different about water is it has a very large, unusually large for its size. Remember, it's a very small molecule. Its molar mass is only 18 grams per mole. It's super tiny, right? But it has a really huge heat of vaporization and a really huge heat of fusion. It also has really large heat capacities, both in the liquid and the solid and the gas, all relatively large heat capacities. Again, a darn good thing for us, right? Our globe is covered with, what is it, like at least 3/4 water, maybe a little bit more, right? That water absorbs a lot of energy from the sun and the world around us, right? It absorbs that energy without changing its temperature by a huge amount, right? It's not like the oceans boil every time the sun comes out, right? It can absorb a lot of energy, right? And reflect it back, right? And that's why it's a danger when scientists are observing the oceans and saying, hey, the average temperature of the ocean is increasing, right? That's a danger, right? Because that's our safety valve, right? That's what stores the energy that comes in and then releases it in a slow and controlled way, right? So when that gets too hot, we're losing our capacity to absorb energy as a planet, right? So again, that's all again due to water's weird properties. The water has these unusual properties. So let's go back and connect it to its structure, right? Because there's some neat things about its structure. Again, nothing we haven't seen before. Right? We've seen this drawing of water before. We've drawn the water molecule. We've drawn its Lewis structure lots of times. We know it has a bent structure. We know the angle is a little bit less than 109.5. It's about 104.5. We know it's very polar, right? We know the oxygen is greedier than the hydrogen. We know there's a permanent dipole moment, right? Oxygen's the negative end of the molecule, hydrogen's the positive end, okay? remember what a hydrogen bond is. Right? So a hydrogen bond has a direction to it. It's the only intermolecular force with a direction. And water can form two hydrogen bonds, right? Because it has two hydrogens that are being unfairly shared, and each oxygen has two lone pairs. So it's kind of the maximum amount of hydrogen bonds that can form. Okay? Those are very strong. So let's look at that picture right under our molecule, right? And it's comparing what's going on the right is hydrogen bonds in water. So remember, in water, things are a little disorganized, right? Those molecules are swimming around and they're forming hydrogen bonds in certain directions. And then they're unforming and reforming again, right? They kind of have a lot of kinetic energy there. So the water molecules can be relatively close together, right? With those hydrogen bonds forming and unforming and reconnecting. When we get to the solid, those hydrogen bonds then, those intermolecular forces that have a direction, they get locked in. They get locked into a position because there's not enough kinetic energy to unlock them, to break those connections, right? The most stable arrangement is a hexagon, right? It's not a coincidence that snowflakes have 6 sides, right? That stable arrangement of those directional bonds if they're not really bonds, those directional intermolecular forces in hydrogen bonds lead to that sort of structure. Now compare those two, the one on the left and the one on the right. The one on the left is really open. There's a lot of space in there. That's a low density version, right? Liquid water, where the molecules, there's more molecules in the same amount of space, that's more dense, right? So ice floats on water. It's less dense, right? And our penguins are super happy about that over here, right? The people who take care of our roads, not happy about it, right? That problem, that density change is what causes a pothole, right? It fills with water and then it freezes, right? When it freezes, it expands because it's less dense. So it needs a bigger volume, right? That pushes the rocks and the materials or opens up cracks in the roads, right? And now more water can get in there and then it freezes again, right? And then it pushes it open a little bit more. More water goes in, it freezes, it gets bigger until you get a giant hole in your road, right? That's kind of the downside of water's special properties, is it makes potholes for us, right? But it's a very strong force. It's a super tiny molecule. So those forces will let them get real close together. So the surface tension of water is gigantic, right? And disgusting things like this spider down there can walk across the surface of the water, right? You can see how it looks like it's dented down where his little feet are touching it, right? That's the water molecules holding together, right? That's all that's keeping that spider from drowning, right? Is the intermolecular forces of lots and lots of water molecules trying to stay together. They're very strongly attracted. So they don't want to give in and let that spider's foot go through them and break their connection. All right. That's what makes water super special. All right. So that is the end of chapter 12. So that's the last thing that will be on our exam, right? There is a discussion group activity. So I want to give you a couple of options. I can email it to you and you can kind of work on it individually and send it back to me, let's say by tomorrow-ish, okay? Or if you want, I can set up some discussion groups here and you can work on it kind of together in a chat room. So I'll let you decide. I'm going to stop the recording here and then you can let me know either you'll leave or stay.